4 slots, 5 things to put in them. Zig stores the first 4 and then it stops the program. Index 4, length 4, I said the bounce check caught it before it could write over whatever was sitting next to it in memory. This is the problem every dynamic array exists to solve. You rarely know the count when you write the code, so let's build the thing that doesn't need to. So that's what we're building, the thing that doesn't need to know the count. By the end of this, you'll have written a list that grows when it runs out, holds any type you like, and gives its memory back when it's done. About 50 lines, and you'll know why every one of them is there. Start with what a fixed array can't do. It commits to a length when you write it. We want one that buys more room when it runs out. That takes 2 fields. Items is where the elements are. It's a slice, which in Zig is a pointer and a length together. Capacity is how many would fit before we have to buy a bigger buffer. 2 numbers and they are not the same number. Length is what you put in. Capacity is what you paid for. Everything in this video happens in the gap between them. Now make it hold anything, not just integers. In Zig, that's a function. List takes one argument, a type, and returns a type. The argument is marked komport time, which means it has to be known while the code is compiling, and it will be because you write list of U32 yourself. So this isn't special syntax. It's a function call that runs during compilation, and what comes back is a struct with those 2 fields in it, where every element is a U32. Call it with something else and you get a different struct. Same 40 lines, no macros, no template language, or the same language run earlier. Now put something in. Append takes 3 things, the list, an allocator, and the item. The allocator is an argument because the list doesn't own any memory. It borrows yours. Nothing in Zig allocates behind your back, and that is the whole reason this parameter exists. The body is 2 lines. If length has reached capacity, there is no room, so grow. Then move the length up by 1 and write the item into the slot that just appeared. Grow is where the real work is, and it's 5 lines. Ask the allocator for a bigger buffer. Copy everything we already have into it with mem.copy. Hand the old buffer back. Then point items at the new memory and record the new capacity. Read the second line again because it's the one people miss. Growing does not stretch the buffer. There is no such operation. It buys a second one, copies, and frees the first. The bytes move. That is what growing is, which tells you the cost. Every grow copies the entire list. So how much extra to buy is a real decision. Too little and you copy constantly. Too much and you're holding memory you never use. What Zig's own list does about that is a whole video by itself, and it's the next one. For today, ask for a bit more than you need, and it works. One thing left, and it's the one a garbage collected language never made you think about. We bought that memory. We have to give it back. dinit takes the allocator and frees the whole buffer, not items, which only covers what we filled, but everything we paid for. Then it leaves the list empty. You call it with defer on the line right after you create the list. Defer runs when the scope ends, whatever happens in between. So the free sits next to the thing it frees, and you can't lose it down a branch you forgot about. And if you do forget, Zig tells you, watch what happens when I take that line out. In debug, the allocator remembers every block it handed out, and at exit, it prints the one that never came back. 132 bytes allocated in grow, called from append, called from line 8 of main, not a crash. A report with the line number telling you exactly which allocation you dropped. One thing you need before any of this runs, and it's the piece most tutorials skip. Where does the allocator come from? Not a global. In Zig, you're handed one. Main takes a parameter now, process init struct, and GPA is the general purpose allocator inside it with leak checking already switched on in debug builds. That is the allocator we've been passing to append this whole time. Nothing was hidden. It came in through the front door of the program. So let's run it. 5 items in, length 5, the case that killed the fixed array at the start. 1,000 items in length 1,000, last item 999. It grew 9 times getting there, and we never thought about it once. And because it's generic, the same code holds a struct we invented 30 seconds ago. So let's put the whole thing on the screen in the order we built it. Two fields, the function that returns a type, append, and the grow it calls when the buffer is full. Dinit and the private helper it frees through. 50 lines, 36 of them code. Pause here and copy it. It compiles on the version in the corner, and it is genuinely the shape the standard library uses. 4 slots and 5 things to put in them. Now the fifth one fits. So does the 10,000th, and you know exactly what it costs to make that true.